It is my distinct pleasure to introduce our next esteemed speaker, Mr. Josh Galloway, a seasoned AI consultant with a rich background in process engineering and advanced process control. Our speaker's experience spans across implant operation, corporate operation excellency, and consulting roles, demonstrating a comprehensive understanding of the field. After completing a master's degree in applied mathematics with a focus on data science, machine learning, and numerical analysis, our speaker transitioned into data scientist and AI roles. The shift marked a significant milestone in their career, leveraging their academic knowledge to practical applications. With approximately 15 years of industry experience, our speaker has made significant contributions to various manufacturing industries. Their expertise and insights have been instrumental in driving innovation and operational efficiency in these sectors. Please join me in extending a warm welcome to our distinguished speaker, Mr. Josh Galloway.
Well, thank you for the intro. May I share my screen?
Yes, you can.
Yes, we can see that, sir.
Good. So as was mentioned, I'm with Schneider Electric. I'm a principal AI consultant, and we work at Schneider Electric, our specific team under Dr. Jurgen, to leverage engineering backgrounds to sort of enhance data science and machine learning skills. So one of the projects we took on recently involved chemical additives in a manufacturing, industrial manufacturing facility, and that's sort of the subject of the talk. So AI-driven chemical additives optimization. So what are these things, right? Many manufacturing operations rely on additives to enhance efficiency and performance of their process. Some of these can be like biocides that kill off living things in your drinking water, anti-fouling agents that maybe keep boiler tubes from becoming scaled and less efficient, air entrainment agents, surfactants, flocculants, you can go on and on. These additives are quite costly, and the optimization of their dosage can result in significant savings for the manufacturing operator. A lot of the times, these chemicals are even, their dosage is controlled by the seller because they're sort of an adjunct to the normal process. So you can imagine there's sort of competing objectives in that case. Pardon. So in addition to sort of the research and development side of this, we did do a proof of concept at a plant who has not volunteered to share any of their information, unfortunately. But it was a seawater desalination plant, an RO process, which means they filter water via the reverse osmosis process through a mesh, basically. And then the pre-treatment section of these plants was the target of our study. And the purpose of the pre-treatment plant is to remove basically all the big stuff that would otherwise damage or decrease the efficiency of the RO membrane. Typical chemical additives for this process are biocides because it's seawater, and then coagulants and flocculants. Some of like ferric chloride and various polymers are used for these purposes. Biocides are dosed intermittently, just on a schedule, and then the residence time of the process is used to kill whatever bugs may make it in from the seawater. So there's not much opportunity there. The coagulants and flocculants are dosed continuously, and so they were targeted for optimization. The data sets and we were given for the POC And for just any typical manufacturing data set, you'll have distributed control system or SCADA data that is typically high frequency, once a second or higher, depending on the operation, and is very, very high dimensional, you know, hundreds more variables and sort of laid out in the information flows, right, like the product flows. So from start to finish, there's an offset. Typically, we downsample this to 1 minute because we're not interested in dynamics that are on the second or millisecond level for steady state optimizations. In addition to this, you'll often see laboratory tests that are done infrequently. Um, for our POC, it was done every 4 hours, but they're technically undersampled for the process that they're representing. So if you can imagine a process that moves rather quickly, can change in 30 minutes, and you have 4 hours, you know, there's multiple paths that can get you from one point to another. So we have to infer uh, what happens in between, and that sometimes can be a project in and of itself. Um, Typically, though, these are the most important KPI for whatever process is under investigation. P&IDs, piping instrumentation diagrams, these show the flow of information and the placing of the sensors and data in between throughout the system. So if you imagine it as a sort of graphical network with these instruments placed throughout, we need to understand what order things come in, or else causality is lost. For our POC, we received roughly 2 years of data. And as I mentioned, the laboratory data was taken on a 4-hour cycle. So for feature engineering and data set augmentation, we start with basic engineering calculations. So having a background as a process engineer, we convert the raw data set to more basic KPI or efficiencies, specific usages, which is the feed flows or having all the dosages normalized to feed flow or production rate. So following that, as I mentioned, you can imagine these plants as sort of a graphical network, and in between are time lags. So if you have a pipe and a certain consistency or concentration of something, the transport time it takes to get to the next sensor where you have information is a pure dead time offset. So in order to align these data sets temporally, we have to do a correlation study and base it on engineering knowledge and the P&IDs to align the data such that it basically makes sense to all our algorithms. And so following that, feature selection is done during basically normal methods, statistical filtering followed by recursive feature elimination. For the model for this project, we chose somewhat novel structure, and we'll go into reasons why later. But the idea is your typical sort of regression optimization and recommendation is up on the top in sort of a peach color. And this is, you know, a predictive model, any black box constrained optimization, and then it produces a recommendation. We also use an operational window, and what this is basically a subdivision of the operational sort of space into operational modes, and then ascertaining a historical best dosage from that and defuzzifying it and producing a recommendation. And then we take an affine sum of the two, which is not optimal, but based on other factors. So with the predictive modeling approach, you use whatever KPI. In the case of a desalination plant, it's things like turbidity and turbidity, basically. And then the input decision variables are whatever you'd like to control. So in this case, it was the flocculants and coagulants. And so then you just perturb, given a state of the plant for all the other input variables, you perturb the decision variables to find an optimal solution subject to whatever operational constraints the plant has provided. With the operational window approach, we label, like I said, all the operational modes within the plant. So say if, going back to the desalination plant, if the water is very warm one day versus cool another, and that cycle repeats itself yearly, which you can imagine is the case, those are different operational modes. And so under those conditions, a certain dosage was used in the past, and we can use just descriptive statistics to find a lower quantile and recommend that, hey, you were here last time in this operational mode, you use this much chemical, you should be able to do it again and increase your savings. With the ensemble approach, we went an extra step. So laboratory data is highly available, meaning it's always, it always works because they just send a guy out to take a sample and then they do the data, and you get your lab samples every 4 hours, almost no matter what, right? Except if the plant is down, and then you can't optimize anything. For the DCS data, especially highly complex analyzers such as turbidity analyzers are harder to maintain, and they're subject to instrument drift that you would have to compensate for somehow. So in order to make the system more robust and actually more explainable, we separate the lab data and the high availability DCS instrumentation, things that are very, very simple to keep working, and use that for the operational window. And then for the regression predictive model, we use the less available, but higher frequency data to produce that model. And then in combining the two, it allows us through the affine sum to tune one way or the other based on the availability of the instrumentation or lab data. So you can imagine, well, we sort of went over this already, but with the more frequent data, you can provide more frequent recommendations, and through the optimization, instead of descriptive statistics, you could actually find a corner and produce both a more optimal answer to the question, what should my dosage be? And you can arrive at a more frequent recommendation, which allows them to change with changes in operational mode more readily. So they can track real conditions easier, which will also save dosage of the chemical. Through the operational window, as we mentioned, it's more robust, but it's also highly explainable, right? So based on the clustering, we can tell the client, you are in this mode. These are the inputs to my model. This is what defines your mode. And this is the distribution of your chemical usage over the last 2 years. We want you to be in the upper quantile or not upper, lower quantile or lower 15th quantile or whatever number they allow us to pick. And we can go from A to B. Whereas with the black box neural network, we can't do that as much. And this helps with comfort level for operations because sometimes adoption of these methods requires a little hand-holding. So to make sure things actually get utilized, it takes some explaining. So for the POC, the predictive model was a temporal CNN. We tested and rated on R2 score. It's based loosely on the WaveNet structure, but as you know, 2016 is millennia ago in machine learning technology. So there were some augmentations that I made to that model that helped get our model more accurate. And we were able to achieve an R2 score of roughly 92%. The optimization, you could use basically any derivative-free or black box optimization needed. Our search space was actually rather tiny, so we just did grid search. But of course, GAs, Nelder-Mead, Bayesian optimization, all of these would work in a larger space. The goal is to minimize chemical usage or cost, right? Because even though you have flocculants and coagulants, I think the coagulants cost about 30 times what the flocculants do. So the sum of the two is your total cost, and then it's subject to KPI constraints, equipment limits, which means how much dosage can you deliver, and then process design constraints that sort of go around limitations of the operation. And this is the sort of general structure. For the POC, we had past values of the KPI, the seawater analyzers, volumes of water processed by the various filters in the pretreatment plant, and then some other sort of esoteric unit run filter is flow normalized to filter surface area, things like this. So roughly 50 input variables that define the process, and then just 2 decision variables used for optimization. And then our output is a recommendation at a horizon of the plant's choosing, or whatever the data set will support. For the operational window, we picked a model based on silhouette score. It was arrived at empirically that we would use Bayesian Gaussian mixture models. There were a couple of models that slightly outperformed it, but the vector of probabilities from the Bayesian GMM allow for a defuzzification method. So it was picked for convenience, basically. We were able to arrive at a silhouette score of 92-ish% again with that model. And then the recommendation worked. We cluster the operational mode, and then from that, we get historical best chemical usages for all clusters. And then to reach a recommendation, you take the probability vector times the historical best chemical performance and dot them, and that is sort of a rough defuzzification and gives you a recommendation. So for this model, you have the structure again. We have seawater labs, filter inlet outlet labs, pretreatment labs, and then a few selected information or instrumentations, things like temperature and pressure that are easy to maintain. And then in all, it was roughly 60 features. Our output is that cluster probability vector, the past best usages under each condition, and the distribution of the important input variables that allow us to make the model explainable. And so ensembling, we tune by affine sum. We didn't do it to produce a better prediction metric. Here, it's to increase robustness, explainability, and allow a parameter to be tuned to the operations confidence level with our solution. So you can imagine, I mentioned the predictive model is based on instrumentation that's not highly available or reliable. So if your instrument is down 25% of the time, then you can only provide a recommendation 75% of the time, which means you'd have to turn your solution off if they can't maintain that analyzer. So under these conditions, we can tune it 100% to the operational window model and then use the lab data to still provide a recommendation, and our solution stays online. Early in deployment, it's typical that operations may not trust your solution because they've never seen it before and they're not necessarily privy to AI solutions in general. So under these conditions, we can tune it again more towards the operational window such that we can explain what our solution is doing and why, which allows them to gain confidence. And then eventually we can tune it more towards the prediction model and give maybe a better, more optimal recommendation. And so results. The analysis of 2 years of data last month held out for testing. 2 chemicals that we selected for optimization, flocculant and a coagulant, with a KPI upper quality constraint, so turbidity can't go above a specific quality where they can't drink the water. We tuned 25% predictive model, 75% operational, and under these conditions, based on the actual dosage they used during that last month and what our recommendation would have been over that last month, we saved them 5 to 7% chemicals over the course of that time. And then we're not allowed to share actual numbers, but if you can imagine just a general RO plant running 500,000 gallons a day of water for 350 days a year is a typical number used for plant uptime. If it's even a small savings aggregated over that time period can result in millions of dollars of savings. So we looked at what these chemical additives are and what the need for a solution is. We looked over how we did the pre-processing with engineering calculations, time lags, and then typical ML feature selection. I explained the impetus for the predictive modeling and operational windows ensembling and why we did it. And then we shared the results as best we could from the proof of concept. And that's my talk. So are there any questions I can answer? If not, I can turn over to whomever. All right, then. I appreciate your time, guys. Thank you.
Thank you, Mr. Josh.